So hi everybody, today's lab is all about simple pendulums. So just to remind you, a simple pendulum is a point mass that's connected to a string, and the string is assumed to have negligible mass when we talk about a simple pendulum. So we learned in class about a pretty straightforward formula that describes the period of a simple pendulum, and there are a couple assumptions that we make when we derive this formula, so let me remind you of those. So first, we're assuming that the oscillations are small. That means that the angle our pendulum achieves relative to the vertical is always a lot less than 1 radian. So small angles, small oscillations. The other thing that we assumed is that there aren't any damping forces. So damping forces are things like friction or air resistance that can remove energy from our simple pendulum. We're assuming that those effects are completely negligible and we're going to ignore them. So, under those assumptions, we derived the period, or a formula for the period of the simple pendulum, which is 2 pi times the square root of L over G, where L is the length of the pendulum string, and G is the acceleration due to gravity. Okay? So, what we're going to do in today's lab is see how an actual simple pendulum works. We're going to look at what are the factors that affect the period, and does the period actually follow the formula that we derived in class? So that's what we'll look at today. Okay, so this is the experimental setup. First thing to note is that we have a vertical stand, which is connected to the table. And then at the top of that stand, there's a horizontal bar. And then at the end of that bar, we have a string. That string is connected to a mass, which is down here. And also connected to that horizontal bar is a protractor. So this is basically what we're going to do in every single trial of the experiment today. We're going to take the pendulum mass and displace it from this equilibrium position by some angle, and we'll be able to measure that angle using the protractor here. Then we're going to let it go, and then watch it swing back and forth 20 times, so 20 cycles. And then we're going to time how long it takes to undergo those 20 oscillations. From that, it's very straightforward to calculate what the period is for a single oscillation. So the reason we do this, why we let it swing back and forth 20 times instead of just once, is you can get a much more accurate estimate of the period that way, since we're averaging over 20 cycles rather than just a single cycle. So the first thing that we're going to investigate, the first factor that might affect the period that we're going to investigate is the starting angle of the pendulum. So the idea is we can set the starting angle to whatever we want, let the pendulum go, watch it swing back and forth, and measure the period. The question we're trying to answer here is, does the starting angle have any effect on the period? And if so, what does that affect? So we're going to start with a very small starting angle, 5 degrees is what we'll start with, and then we'll measure the period. We'll increase the starting angle, measure the period again, and we'll do this several times to try to get a sense of, again, how that starting angle might have an effect on the period. So there are some factors or some variables that we're going to keep constant in this part of the experiment, and that's going to be the length of the string for one. So the length of the string is 60 centimeters in this case, and we're also going to keep the mass of the ball the same. So this is a steel ball. We're going to keep using that same exact mass throughout this experiment. So let's start with 5 degrees as our initial angle. And I've got it set to 5 degrees right now. As soon as I let go of the ball, I'm going to hit start on my timer. Then we're going to count out 20 swings back and forth. And as soon as we've seen 20 swings, I'm going to hit the stop button and we're going to get the time. Okay, so here we go. 5 degrees and go. That's 1 swing, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so that's 20 swings. the time for those 20 swings was 30.92 seconds. Okay, so when the starting angle was 5 degrees, the time for 20 swings was 30.92 seconds. Okay, so the next thing is to do it again, but for a larger starting angle. So now I'm going to set the starting angle to something bigger, 10 degrees. Okay, so here's 10 degrees. And it's the same idea. I'm going to let go. As soon as I let go of the ball, I'm going to press the start button. We're going to count 20 swings, and then we'll see how long it takes to do those 20 swings back and forth. Okay, so here we go. Start. 1 swing, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so take a look at that. Almost the same exact time. For 20 swings, when we used a starting angle of 10 degrees, 30.99 seconds is what we get. So 30.99 seconds. So for this part of the experiment, we're going to just continue on in the same way, increasing the starting angle each trial, measuring the period each trial, and trying to get some kind of sense as to whether the starting angle has any effect on the period, or it might not have any effect. So we'll continue increasing those angles until we hit 75 degrees, and we'll just stop there. I'm not going to show you all of those trials on the video. I'll just flash the data up on the screen right now. So in this part of the experiment, what we're going to be doing is looking at the effect of the mass of the pendulum on the period of its oscillation. So a number of things are going to be kept constant throughout the experiment here. The first is the length of the string. We're going to keep that at 60 centimeters. We're going to keep it fixed. We're also going to keep the starting angle that we use fixed at 10 degrees. And what we're going to be changing is the mass. So we have 3 different masses. We have a wooden ball that you see here. We also have an aluminum ball, which has a greater mass than this. And then finally a steel ball, which has the most mass. Now we've already taken the data for the steel ball, so just use that in this experiment. Now I'm going to show you what happens when, again, we use a 10 degree starting angle, 60 centimeters of length, and we have a wooden ball. So let's get the timer ready. Let's get the starting angle to 10 degrees. And go. That's 1 swing, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, so the time I'm getting here is 29.77 seconds for 20 swings when we have the wooden ball. So there's actually only one data point left, which is how long does this take when we're using the aluminum ball. I'm not going to show you the video for that right now. I'm just going to flash the data up on the screen. Now, for the last part of the experiment, what we're going to be doing is trying to see what effect the length of the pendulum has on the period. So we're going to be keeping the mass the same. We're going to be using the same steel ball the entire time. We're also going to be keeping the starting angle the same. We're going to keep that at 10 degrees. We're going to change the length of the string during each trial. So we're going to start with 100 centimeters, which is what we have here. That's the length of the string. And then we're going to decrease that in 20 centimeter increments. So we're going to do 80 centimeters, 60, and so on until we get to 20 centimeters. And at each time, we're going to measure the period. And again, the idea is to see how the length affects the period. So starting with 100 centimeters, let's get the timer ready. And let's start the pendulum at 10 degrees like this. And here we go. Go. 1 swing, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay. So for 20 periods of oscillation, the time we're getting is 39.45 seconds. So when the string is 100 centimeters long, the period for, or the time for 20 periods is 39.45 seconds. So now I've changed the length of the string. Now we've got an 80 centimeter long string here. And what we're going to do is measure again the time for 20 periods of oscillation. So, okay, we've got the starting angle at 10 degrees. And go. 1 swing, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, there it is. So the time for 20 swings when the string has a length of 80 centimeters is 35.76 seconds. So the rest of that experiment pretty much goes in the same way. Each trial, the length of the string is going to be decreased by 20 centimeters, and then we're going to measure the period of the pendulum. So you're going to have some kind of idea after you take all this data what the effect of the length of the pendulum is on the period. Now, I'm not going to show you the rest of the trials. I'll just flash those up on the screen here. So here they are. All right, so the last set of measurements we need to take are the masses of these 3 different pendulum balls that were used in the experiment. So let's start with the wooden ball. That was the lightest one. And the mass of this one is, let's see, it's very, very light. So to get the scale to balance out, for the wooden ball, we've got about 4.6 grams. Okay, so 4.6 grams for the wooden ball. The next one is the aluminum ball. That was the sort of the middle one in terms of the mass. So let's see what we have here. So it looks like it's more than 20 grams, but less than 30. All right, so for the aluminum ball, to get the scale to balance out, the mass is about 22.2 grams. So 22.2 grams for the aluminum ball. And then finally, let's do the steel ball. This is the heaviest one. And okay, so this one's more than 60 grams, less than 70. All right, so to get the scale to balance out on this case, in this case, we have 67.1 grams. So for the steel ball, the mass is 67.1 grams. So that does it for the lab. You've seen all the experiments, you've seen how they go, and all the data that you need to do the analysis is collected. So The worksheet that accompanies this video is going to explain the analysis you need to do to complete the lab. And there's one calculation in particular that I want to point out. Based on the data we collected here and how long it takes for the pendulum to swing under different circumstances, you are going to calculate g, the acceleration due to gravity on Earth. Now you know that the sort of accepted value that we've been using all this time is 9.8 meters per second squared. So what you calculate based on the pendulum data should very, very closely agree with 9.8 meters per second squared at the end of the day. So that is one thing you should look out for, is close agreement with the accepted value of g. So that's it. I'll see you in the next lab video. Until then, be safe, be healthy. See ya.